Hi everyone, I'm Matt. So I'm going to be talking about how you can kind of deal with failure in like kind of concurrent systems, which goes particularly good at. Little introduction, I work at an actual bank. Not quite a bank yet, but like hopefully will be very soon. And one of the issues that we have is that our systems need to be extremely reliable. If you go to a cash machine and your bank card doesn't work, that's a problem. Or if you go to a shop and try and purchase something, then again, like it's a really bad customer experience if our systems are kind of failing or not responding in a kind of timely fashion. So it's very important that our systems deal with failures. And there's a number of ways that we can do this. Usually we'll want like highly available systems, so we'll be running multiple kind of copies of every kind of particular piece of software. And we're generally running them as like a distributed system. So we'll be running across multiple machines, potentially multiple data centers, which introduces a whole raft of different problems. So there's a little diagram, which is actually from Halo's infrastructure. Sorry guys, which you probably can't see, but like when you have a distributed system made of a large piece of components, like it's really complicated. There's like so many things kind of interacting, things time out, and you need a way to kind of encapsulate that complexity. So a good way of doing that is by breaking your system into lots of small pieces. They're kind of very simple then, they have like a bounded context, they only operate on like one kind of thing with like a single responsibility. And Go's particularly good at that. So obviously we can build all our code and compile it, and we get a single file, a single binary that we can drop onto servers, and we can run that pretty much anywhere. So that makes kind of deployment and operations quite easy. Obviously its concurrency features are really good, so we can quickly spin out loads of Go routines to kind of deal with all sorts of different things. And if you're building like highly concurrent systems where you're dealing with like quite high throughput, that's obviously really good because you can handle large volumes of requests at the same time. But there are a large number of like, I don't know if anyone's seen a blog post called like fallacies of distributed systems. There's huge numbers of problems you have if you're running across lots of machines or you've got lots of components. Machines fail, inevitable. You have network partitions, that's kind of inevitable. You'll also get like latency spikes, especially if you run on like kind of virtualized networks. And you also get like lots of really weird interactions where like a machine might be really busy and that might appear that it's actually timing out. So it'd be the same as having a network partition, but actually it's like totally fine. It's just like really, really busy. So if we dive into some Go, I'm sure everybody has seen and dealt with this. So one of the great things about Go is that it kind of forces you to deal with your errors, which is really good. And we can do a lot of things around this. So if we've got like some kind of basic method that we'd like to work, we can like deal with the error and kind of deal it with there and then and return early, and hopefully kind of respond successfully back to the client. And we can abbreviate this a little bit. For anyone who's not used a huge amount of Go, you can make it into like a single line, and we can like kind of deal with the error right there and then carry on if everything's okay. But our real question is like, what are we going to do with this error? Are we just going to return it? In which case, whatever is called our method needs to kind of understand how to deal with the error. Obviously, if our function signature is slightly different, we might be returning like the nil type for whatever thing we actually wanted. So it might be nil, it might be a blank string, some kind of basic, the nil type for that particular type. Or we might return like an error that we kind of construct. So if we like kind of construct a string using the thumped module package, we could like construct a nice error around that. Problem is, if we're like doing this, we had an error before which might have been quite like descriptive, and then we've like sorry. So we might have had an error which was quite descriptive, and it might have had loads of extra information because you can pass custom types around that have the error interface. So if we like smash that into a string, we've lost all that extra information. So if we are like making some kind of HTTP request to some website, we're going to get our response back, and if we got some error while we were getting that website, we're just going to like stick that into a string, which doesn't really help the person who then gets that error. So we have no way to determine what that error was unless we're doing like string matching, and that would vary on every single one. So we could return like standardized strings. Using something like the fun package, we can just return an error, and this will create a new error exactly the same as this, and pass the error back. But we could take that a bit further. We can create like defined errors in our packages, and then we can return those. So we could return a particular error, and then actually, if these are exported from our package, we can compare against them in some other caller. And then we could just return this instead. So if we're like loading our website, which was beesbeesbees.com, you should check it out, then we might actually just want to pass the error back and assume that the caller will deal with that. Or we might want to like pick out particular errors that we know that we can handle. So if it's a timeout, we might choose to retry, hopefully with some kind of retry strategy. Or if it's not found, then it's never going to succeed, so we may as well abort straight away. In which case we might just return the error back to the caller. We can have default cases, so we could just pick out specific errors, return all of the other errors back to the caller. In which case we can like start to simplify this a little bit. But then we kind of might end up in some horrible place where we're like constantly retrying our thing that we called. And this is like really bad for the thing that we're calling on the other end. So if we are literally timing out and retrying without any kind of back off, like we're literally just like get some form of HTTP error and we immediately retry, and we're in like an infinite loop here. So if the site's down, like we're never going to jump out of this, and we've also like multiplied the traffic to our failing component. So really we want to like kind of deal with this in a slightly better way. We want to kind of possibly retry, maybe not. If we are going to retry, we certainly need to like think about how we're going to retry. Are we going to like have some kind of exponential back off where we gradually increase our timeout period up to a certain point, and then only do a certain number of attempts and then finally give up after that? We should definitely kind of limit these things. So what are we going to do if we have a timeout? So in the HTTP module, you might not be able to read this, we can, the default client, you can set deadlines on. So we could take a standard HTTP connection, build a new client, and potentially build a transport with a custom dialer. And there's really kind of two parts to this. There are actually two timeouts that we're trying to catch. We're trying to catch both a connection timeout to the other server. So if the server's not responding at all, we might block until we're like actually connected, and then the request might be very fast. But our connection might be really quick, and then the server may block forever. I've kind of worked on systems where you connect, and then the guarantees are that you get a response within 60 seconds, which is like really, really long. And like I usually work on mobile apps, so I can't really have like a mobile app where the customer presses something and they wait 60 seconds, it's still not working. I'll press it again. And now I'm like kind of multiplying my traffic inbound from my client potentially. If like people are hitting F5 when sites are down, like just refreshing every time. So we need to catch kind of both of these timeouts. And we can do that by like creating a new client. We can create a custom method as a timeout dialer. And then we can pass in both like a kind of connect timeout and a read-write timeout. And then pass this into our connection. When we actually initiate the connection, we'll time out after a period of time. And then if we do connect, then we want to set a deadline for our corresponding server to actually send us a response. In which case we would probably like give up at some point and hopefully present some nice happy message back to the user. And there's a lot of example of this in the real world where so Netflix do a huge amount of this, where if I open up my Netflix app, then I get like personalized recommendations, and if the personalized recommendation system isn't working, then it'll kind of fall back to like less personalized recommendations, things like ones that are based in the UK, for example, if I'm in London. So there's a large number of things we can do kind of with timeout errors. So on the other front, that works if we're like using, say, the HTTP package, where we can actually pass in timeouts. All this stuff exists already. If we've got our own code, then we kind of need to be able to build these things in. So if we are, again, we've got some method that is going to do some work for us, and it's going to return a slice of something. You'd probably have some kind of error catching here as well, obviously. And we're going to assign that into a variable. So at the moment, this function call is going to block indefinitely until the function actually completes, which if we are running in like a HTTP handler, the client will have gone away after a short period of time. But we're still using our server resources kind of executing this operation. So we could like start to refactor this a bit to use kind of Go routines. We can use channels to pass our results around. So instead of doing this, we could fire our method in a Go routine and then wait on the channel for the response. And that means that we can like do more interesting things in our client. So we have a Go routine that's running, loading all our bees from bees.com, and we can then use like a select case. So we can put this in a select where we try and assign, we try and read off the channel, but then after a certain point we have the time.after method, which will fire, gives us another channel. So there's a few methods in the time package that do this, tickers notably, but also time.after will give us a channel back, and then after that period of time it will fire something down the channel. So we can very easily, with like a couple of lines of code, time out this method and then kind of respond back to the client with some kind of nicer error or potentially a fallback. So if we had potentially cache data that we could use, we might store that in memory, and like best case we load fresh data, but like worst case we respond with out of date data by 30 seconds or a minute or something. And in a lot of use cases that's probably okay. So when we do that, we're going to presumably respond with our timeout error. Again, we can use all of our particular error values, and just like fire this back after a second. Second's probably quite long. All good. But the main problem we have here now is that, as I said, we're not actually dealing with any errors that come back from the method. So if we were just calling this as a function, we'd have like bees, thing, and we'd like get our error and we'd immediately deal with it, and that's all good. But if we just have a channel that's like sending our response back, we have no way to get our error, and we're not blocking deliberately. So in a lot of cases we might kind of pass something in and get a reference back to it. It's not really the best way of communicating between our Go routines. So there's a couple of other options. We could, rather than just passing a result channel into our method, we could pass two channels. We could pass like a result channel and an error channel, and then we could select on both of these and do different operations on the response. The other option is using an anonymous struct. So I don't know if anyone's used structs like that before. So we can define a struct without having defined it actually as a type, and we could just have it with two values. So we would just kind of pass both values into this struct and pass that down our channel. And at that point, we can then actually check, like, if it's an error, do this. Otherwise, if we actually got our result, do something good with it. So when we're doing this, we literally got our timeout, and we can do these two things. However, if we do timeout on this, we have a small problem. Our select case now is no longer listening to our bchan, so we're not going to get, we don't have a reader of this channel, and that means that the go routine we fired a minute ago will block indefinitely. So we have no way of getting a response back off that channel. We're not listening, we've timed out, we've gone back to the client. So really we want to kind of make this non-blocking as well. And that's really easy to do. You can just make it a buffer channel. So we're going to have one result, we'll stick it in the channel, and then even if our reader has gone away because it's timed out, our writer can still put the result in, and then it will fall out of scope and be garbage collected. So that's like a pretty easy way to deal with kind of synchronizing both readers and writers. So something a bit more real world. Who here uses RabbitMQ? Anyone? Loads of people. Everyone at Halo does. So RabbitMQ, as like all kind of messaging systems, databases, you're going to need to connect to a server at some point. So you're probably going to connect. You're probably going to get an error at some point, and hopefully, because you're just trying to connect, you would again retry. Although again, with some kind of retry policy. So a very naive implementation might be literally to put this in like an infinite loop. We're just going to like connect, and if it connects, great. And if it doesn't connect, we'll just like loop back around, reconnect. And if our binary is running for like weeks, then we should be connected most of the time. Obviously, we do that with some backoff. So if RabbitMQ is like really, really slow, the servers are really heavily loaded, we've got all sorts of problems going on there. We don't want like thousands of clients continually reconnecting all the time just because their network dropped. So we would again want to probably have a number of attempts and then have some kind of exponential backoff where we kind of tracked how many times we've connected, and then once we've successfully connected, maybe kind of after a while wipe that timer. And if you use, I've used Sean Treadway's MQP library for this, which gives you like a really cool little feature. So once you've connected, you're going to like get, you can get a channel back from this, which will notify you when the connection to RabbitMQ closes. So we can like connect, probably connect a few times, maybe like fail, continue, kind of loop round, and then at some point we'll connect, fingers crossed. At which point we can like come down to the next stage, and we can just like block here indefinitely. So at this point, this con notify close returns a channel. Currently there's nothing on that channel, so we'll just sit here. And then if RabbitMQ disconnects for whatever reason, it'll fire something down that channel. So we'll immediately unblock, we'll actually get an error. We could like log that, do something clever. And then in this case, we'd spin back round and we'd attempt to reconnect again. So we'd again have this kind of go routine that's kind of running and it's connecting and it's dealing with our connection in the background. So that kind of works quite well, but we might again want to do slightly different semantics around this. So we might not just want to like kind of block on being disconnected. For example, if our configuration changes, we might want to like reinitialize our client. So if we pop that in a select, we could then have like some kind of configuration change. So we're going to connect. Once we've connected, we'll then block until either we disconnect from RabbitMQ and then we'll reinitialize, or if we get a config change. So say we had some other Go routine that is monitoring our configuration, maybe like environment variables, maybe from some remote configuration system, and as soon as it notices a change, we just fire like a message down this channel. That would unblock this, and then we'd reinitialize our connection. And we could do other things there. So we could have a quit channel, in which case, if we got anything down that channel, we would just return, and our connection, we'd probably want to tear down our connection first, but we could just return back out of there and shut down cleanly. Except actually in the case of channels, we don't need to like fire something down this. In the case of a quit channel, this is something we're going to use once. So we could create a channel and then kind of do this somewhere else, and we're sitting there blocked on our channel. And then if we close the channel, it will immediately fire. So it will no longer block, and we can go straight through and return. And that's like a very nice way of kind of synchronizing and coordinating across our Go routines. So we can like start kind of building this out. We can like block until we get a configuration change, until we want to shut down, or if other things happen. So one of the systems I used to work on was an ID generation system. So it generated like 64-bit time-ordered IDs, which like 41 bits time in milliseconds, 10 bits of a worker ID, and 12 bits of a sequence ID, which incremented every time it issued an ID within a millisecond. With such a limited number of bits, you only have a small number of workers that you can have. So you have to be able to very accurately coordinate and hand out these IDs to all of the different workers. So we used to use Zookeeper for this. You can like write something into Zookeeper, get a lock on it. The Zookeeper library has like kind of nice locking recipes. And one of the things you can do in Zookeeper, and you can do in like etcd and a couple of other tools, is you can then watch this value, and if it changes, you can do certain things. You'll be notified when it changes. So in this case, we might actually want to like do something really, really bad when this fires. In this particular system, like, so if you're using something like Twitter Snowflake, if two of the workers have exactly the same ID, they will generate the same IDs. And if you're using those as like unique IDs, then you have like a really, really bad problem. So you might want to like, again, block on a channel, and if we quit, shut down. If we get a configuration change, reconnect. But also if like something fiddles with our lock and that expires, then we want to immediately stop doing things. So we'd want to unblock, stop our work, and reconnect. So we can like tear that down, and that works quite well. So using quit channels and various other channels in this way is like a really nice way of coordinating things. It's really easy to do, but there are like some kind of extra tools that you can use around that. So one of them, I don't know if anyone's used the Tomb library. I know a couple of people have. Cool. So Tomb is basically a wrapper that will wrap a closed channel. And there's a few quite nice semantics, so it has a couple of extra helper methods. So you can like block on waiting for a kill signal, and then when you receive the kill signal, you can do something. But the client that sent the kill signal can wait until all the other clients have exited. And that's again like a really nice way of, if you're coordinating like workers in your application, you might have n number of workers that are kind of taking requests and dealing with things and like doing all sorts of things in the background, and you could like kill a particular remote Go routine, which is usually quite hard to do, and that's like quite nicely encapsulated in this library. So there's a lot of kind of semantics obviously on reading off channels. Writing to channels again is very similar. So if we're going to write something into a channel, that's going to block by default unless there's something at the other end. And you could have like a channel of bools. Actually, quite nice semantic is to use an empty struct. It's a bit more efficient. In which case, I think the name Brad christened the other day was struct curly 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 for this. So we can like fire a struct into our channel. And again, if we want this to be non-blocking, we can like set capacity, make it buffered, or we can use a select case with default. So in this, we would attempt to write it into our channel, and if it's not possible, then we'll like kind of abort, and if it would have blocked at all, we'll fire the default case and we'd do nothing. So this is quite useful if we want to like observe something. So again, using like a configuration system, we would have potentially one Go routine that is monitoring a remote configuration system. We might have like quite a few users of that within our binary, in which case we don't want each one of them to have its own connection to a configuration system, just to monitor like this section of our configuration, that section of our configuration, etc. So we could just create like slice of channels, And then for each one of these, we can then attempt to notify the receiver. So we can just run through each one of the observers, try and notify them. Best case, they get the message. Worst case, we kind of ignore them and they don't. And usually using this pattern, we would kind of notify some of these people. The other ones might literally be processing the previous notification. So they just like spin round, and next time something changes, they'll find out. So, taking this a little bit further, one of the really important things about distributed systems is being able to trace requests as they go all the way through. One of the systems I used to work on, and actually work on, have a new version, is a distributed trace system, which kind of for every like remote call you make between systems, you can describe what's happened, what's about to happen, and then when you get a response, you might file like a timeout, the timing data, that kind of thing. So a bit like Twitter Zipkin, if anyone's used that. And one thing you don't want to do is you don't want your instrumentation to affect actually serving customers. So like, I really like pretty graphs, but I probably prefer that like customers could get money out of their bank than like me having some awesome dashboards I could look at. So if we have like some workers in the background that are processing these things, it would be really cool to be able to like try and send them, but if not, then just not bother and kind of drop them on the floor. So we can do like, we can create some buffer. 200 is probably a bit low, like it's not going to take much memory. We'll initialize a client, which we have like a Go routine in the background that is going to do the publishing, and that's going to read off this channel, kind of aggregate things up and fire them onto our remote system. And then we can use again this like channel semantics. So we can attempt to send, so our interface that we give as a client back to our other programs is like, give us some bytes, we'll like deal with that for you, all good. And best case scenario, we'll like try and put it into this channel, and then our other Go routine will like take that and send it onto our other system. Worst case scenario, we can hit this default case. It ensures that we don't block, and then we've got like no performance penalty on our client. So we can fire these things before and after every single HTTP request or RPC call between our systems, and like we have no worries here. So the other part that we have is on our server. So when we're serving HTTP requests, we're going to use like the net HTTP package, and that's going to like fire off Go routines for every request. It's all good. Rabbit is like slightly rawer, so we're going to get deliveries. Here is a channel of deliveries. So it's going to connect to RabbitMQ, and it's going to read every message that comes in and put it into a channel for us. So we connect. If we have connection error, deal with that. And then we can range over this channel, and for every message that we get off the channel, we'll just fire a new Go routine, which is totally cool. Like, we'll fire that off, we'll have n number of concurrent Go routines running, and they can handle the request and then send some response back. So that works pretty well. But there's a bit of like a problem here. Like, again, if we're running like, if we've got lots of traffic going to different systems and one of them's running particularly slowly, there's like lots of latency on memcache or something, then we might go from like a 10 millisecond response time to like 100 milliseconds, and that might blow something out further up our chain. So if we're like really heavily loaded or we're going much slower, we probably don't want to handle all these requests. We probably want to like shed load right at the top. But we have fired a Go routine for every single request at this point. So like, we're kind of anticipating that we're going to process all of these. Another way we could do this again is just with a channel. So we'll create a channel of structs, say it's 1,000. When we start up our binary, we'll just like, for 1 to 1,000, like fire a struct into that token channel. And then we have like a channel that we can take tokens out of and put them back into. And then we can select on this. So we could like try and select off the channel. And if we can get a token, like we're 1 of 1,000, and then we can execute our request. And obviously we'll put the token back on, and all good. And worst case, like we can't we can't take a token because there are currently 1,000 concurrent requests running. So we can then like return some form of error saying that we're at capacity. And equally, we could do this immediately, which, bearing in mind, like the requests are going to be executed really, really fast. So like, I don't think we ever saw this dip very far down. But if we did want to kind of block for a short period of time, we could again use like a timeout here. So we could wait for up to 100 milliseconds or like 10 milliseconds to be able to start our request. And if that's not going to work, then we can just return immediately with an error. So at that point, like we can potentially shed load at the server side, but we're still receiving requests. And if our server is very heavily loaded, ideally we wouldn't even receive these. That would be much, much nicer. So there's a really good library. I don't know if anyone's seen CircuitBreaker library. Anyone? A few people? No? So this is on GitHub, and it models very similar to kind of a system that Netflix have, and I think Twitter in their Finagle library, which basically monitors outgoing requests and allows you to determine what to do on those. And it can trip on like failures or timeouts or like a particular error rate. And if we use a library like that, then we can actually like create a new client, and we can give it like a maximum timeout for this request and the threshold of errors that we're going to accept. And we could pass in like a custom HTTP client if we wanted to. We're going to go off and get our website, and if this fails lots, then it won't even make the request anymore. It will just like return with an error immediately. So that kind of sheds load off our server and like lets our client be a bit smarter with this. So yeah, as like a more kind of traditional enterprisey company, you'd think like, why would a bank like choose to use Go? And for us, like it makes our developers really productive. It's incredibly performant. The concurrency gives us a huge amount of control over how we're going to like deal with requests between our systems. And as a result, we can make our systems a lot more reliable. And that's about it. Any questions? No. Good.
How do you find, so setting a timeout is good because you can control your execution, but how do you find time selection? Because the Go routine that you speak is still consuming resource even if you set the time.
Yeah, so the question was if you have received an inbound request, you've already fired a Go routine to deal with that. So if you are waiting on that request, even though you were bought, that request is still going. And yeah, that's totally true. You can build that into your HTTP client, in which case the Go routine will abort, and it just won't listen for a response anymore. Or if you use something like the context package, you can kill requests kind of further down the line.
You mentioned distributed tracing at one point, and
Yeah.
Zipkin in that warehouse. Are you using that, or were you using something custom?
So using something custom, but quite similar to Zipkin. Probably not as many features. I think we're out of time. Yeah, cool. Thank you very much.